We're going to start off by looking at number systems, and this is the ways that we represent values. So before we get too far into it, I want to take 30 seconds here to talk about numbers. And what we know about numbers is they help us count and represent amounts of stuff, right? You're used to the idea of 1, 2, 3, 4, right? That's sequentially increasing the amount of things you have. And we use numeric symbols to represent the amount. So, for example, you might be used to 1, 2, 3, 4, 5, etc. But you can also have things like tally marks, right? 1 through 5, or other ways of doing it. But that's the idea: is we just have a symbol and it represents an amount. Other ways that you might see that is things like 10 to the third. That's a different way to represent 1,000. But what we care about here for this class is bases. And a base is how many symbols a number or a system uses to represent numbers. So the higher the base, the more compact those numbers become. So for example, in base 2, a certain number written like this is equivalent in base 10 to the same number. So these, in their two systems, are the same number. And so we can look at that just like another example might be this number is equivalent to, what would that be? That would be 1 plus 2 plus 4 would be 7. So the difference is in base 2, we're only using two symbols, these 1s and these 0s. In base 10, we can use what you're used to, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's why we can write the same number with fewer digits. So that's all you really need to care about right this second for bases, is that the larger the base, the more symbols it uses, and so therefore the fewer digits it can use to represent a number. So let's look at some of these examples and what they mean. So in base 10, the number 347, or the number 347 here, represents 7 groups of 1. So the far right digit we always represent as 1s, right? If you remember back to elementary school, you've got your 1s place, you've got your 10s place, and you've got your 100s place. And so the second would be 4 groups of 10. And then this third place would be 3 groups of groups of 10, or in other words, 100s or 10 squared. So you can see that each time we go to the left, from the right to the left, we increase it by another group of the base. So the first one is 1s, then we've got 10 groups of 1s, then we've got 10 groups of 10s. The next one would be 10 groups of 100s, or 10 groups of 10 groups of 10s. And if you kind of track with that, all the rest of the bases are the same. So base 2, if we've got this number 1011, it would be 1, we'll say 1, 1. It would be 1 group of 2, 0 groups of 4, and then 1 group of 8. So with base 2, we had the same idea. We have our 1s, but then because we're in base 2, the next column is our 2s group. Then we have 2 groups of 2, so our 4s group. Then we have 2 groups of 8s, 2 groups of 4, sorry. So we have our 8s group. And so you can see that each time we go over, we go up by one more power of that number, or another group of groups. So we'll do one last example here of 456. It's not 456. 456 in base 8. So what do you think this would be? It would be 6 ones. Then this group would be 5 groups of how many? 5 groups of 8. And then this would be 4 groups of 64. Because it would be, each of these should be 8 groups of 8, so that's why we get 64. So we have our places, our place values, we have our 1s, our 8s, our 64s. And then if we had another group, it would be 8 times 64, which is 256, I think. No, that's not right. So whatever that is, 4,000 something or 400 something. Okay, so how to add. It's the same as base 10, but we carry a 1 whenever we get to the base value. So instead of figuring out, oh, I went over 10, you figure out, oh, I went over 8 or over 6 or over 5, whatever the base is. So let's write that out here. 42 plus 15. Well, 2 plus 5, well, if I do 1 plus 5, I get to 6. So that means I'm going to get above my base. So I need to carry 1 because 1 plus 5 would give me 6, which means I carry it. And then I've got an extra 1, right? Because 2 plus 5 would give me 6 and an extra 1. So I put a 1 down here. So just like if it was 2 plus 9, we'd write a 1 down here and a 1 up here. Because we go 1 extra beyond, right? It would go 5, 6, and then reset, and we've got plus 1 extra. So we write our 1 extra down at the bottom here, and then we carry our 1 at the top. So then 1 plus 1 plus 4 is 6, so that means we've hit our base, so we need to write a 0. We carry a 1. And so this would be 101. 42 plus 15, or sorry, I should say 42 plus 15 in base 6 would be 101. Subtracting is the same but as base 10, but we borrow the base instead of the 10. So 42 minus 15 in base 6, well, if we subtract that, 2 minus 5, 2 is smaller than 5, so we need to borrow. So we take away here, and we get a 3, just like we would do in base 10. But then we add 6 on the right here. So we can kind of cheat and say it's like there's 8 here now instead of 2, because we're used to base 10. But really properly, it should be 12 minus 5. Either way, 8 or the 2 above the base minus 5 will give us 3. Then we have 3 minus 1, that one's fine, so we get 2 3. So 42 minus 15, 42 minus 15 gives 2 3. It's a little weird because, again, 42 is a base 10 number, but 42 in base 6 is, a slightly different value. If you're unsure about these, maybe go back and watch again, or when we're practicing, you'll get a good feel for it as I'll help you through things in class. So the common systems that computers use, we have base 10 is common because it's kind of our standard base for most math. That's what you're used to working in. We also care about binary or base 2 because this is easily created physically with switches, electricity, etc. Right? If I have a switch that's either up or down, that can represent a base 2 number. It's either an up, a 1, or a down, a 0. And then I can have another switch that's either up for a 1 or down for a 0. If I wanted to represent a base 10 number, I'd have to have like a dial with 10 positions, right? And so if we have just two things, it's easy to create like an on or off, an up or down, a left or right, a high or low, that sort of thing. So this is why computers use base 2, is because when we were first designing them, it's easiest to make something with, two states. Hexadecimal or base 16 is also used because it's close to base 10, meaning it's pretty similar to what we're used to seeing, but it's easier to convert to binary than base 10 is, because it's just, you take the first collection of digits in base 2, and then you do a quick math thing, and then that's your ones digit on hexadecimal. You take the next chunk, you combine them, and that's your 16th digit. So I'll lastly mention hexadecimal for 30 seconds here because it's kind of interesting. In base 10, we only have 10 symbols. So in math, we're used to working with these 10 symbols for numbers, 0 through 9. But if you're going to hexadecimal base 16, you need 5 extra, or technically 6 extra symbols, right? So what do? We just add these capital letters. So the numbers go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So A is 1 bigger than 9. If it was in base 10, it would be 10. B is 2 bigger than 9. If it was in base 10, it would be 11. But this means we can write up to 15 as in base 10 as a single digit, right? Instead of writing 15, I can just write F. So it's 1 fewer digit. So an example here is this 4E. So if I wanted to convert that to base 10, this is E, so that's 14 groups of 1. And 4 would be 4 groups of 16. And so 4 groups of 16 plus an extra 14 will give us 78. So this is a real quick, brief overview. I know I went through it quick, but I think with the practice, you'll get comfortable with kind of thinking about things. And ultimately, all that matters at the end of this is base 2, and that you get how it kind of relates to base 10.